Imagine reading a piece of sheet music where you are only allowed to play one note at a time. For decades, our traditional computers have operated exactly like this. They process information in basic units called bits, which have to be either a definite 0 or a definite 1. This reliable, single-note logic has been the foundation of every machine we use, from the massive, room-sized mainframes of the past all the way down to the smartphone in your pocket today. Because these computers can only handle one task at a time, they have to check every possible solution to a problem in a long, sequential line. For truly massive challenges, like simulating the complex chemistry of a new medicine, that line becomes so incredibly long that a standard computer would need thousands of years to reach the very end. But what if a computer didn't have to wait in that line? Imagine a bit that acts like a spinning coin that hasn't landed yet, holding the potential to be both heads and tails at the exact same time. This state is called superposition, and the units that use it are known as qubits. If a traditional computer is a single piano key, a quantum computer strikes a massive, complex chord, letting multiple notes ring out simultaneously. And we are actually building them today. Engineers construct these intricate, super-cool devices right now to control these overlapping states. But there is a catch. If a machine processes information as overlapping chords instead of simple single notes, ordinary geometry and standard math simply do not know how to write the sheet music to track what the machine is doing. To solve this problem, physicists rely on a specific mathematical environment known as a Hilbert space. It is named after David Hilbert, a mathematician who developed these rules decades before the first quantum computer was even an idea. This split-screen graphic shows the difference between the math we use every day and the math required for quantum mechanics. On the left, an ordinary physical map plots physical distances, like a house at a specific intersection. On the right, a Hilbert space map tracks what we call probability amplitudes. Think of these coordinates as the mathematical weight or likelihood of each state. Instead of showing where a particle is located, this map shows how likely it is to be found in a specific condition. Looking at this probability grid, every possible state of a quantum system is represented by an arrow called a vector, pointing out to a single precise point. By giving these overlapping probabilities an exact coordinate, Hilbert space provides a stable environment to capture things that exist in multiple states at once. Inside this mathematical space, we have basis states. You can think of these as the individual, pure piano keys of the system, representing a definite 0 or a definite 1. Physicist Paul Dirac created a very specific notation to write these states down on paper. This diagram illustrates his system in action. Instead of traditional musical notes, we use what is called ket notation, written as a straight vertical line and an angled bracket. A 0 inside means state 0, and a 1 means state 1. These serve as the x and y axes of our quantum map. When a qubit plays a chord and goes into superposition, we draw a new line right here between the axes. This shows the state existing somewhere between a 0 and a 1. Dirac's notation acts as a direct translation tool, turning complex quantum behavior into manageable, readable math. A single qubit requires a two-dimensional map to plot its position between 0 and 1. But real quantum computers link many qubits together. This bar chart tracks what happens to the math when we do that. Every time you add a qubit, the size of the space multiplies through an operation called a tensor product. It is a way of mathematically stacking spaces so that every new qubit doubles the amount of information the system can hold. 2 qubits demand 4 dimensions. 3 qubits demand 8. As the chart scales out, you can see the exponential explosion. A system of just 50 qubits requires a Hilbert space with more than 1 quadrillion dimensions. While this math works perfectly on paper, the sheer number of dimensions makes it impossible for a traditional computer to keep track of it all. Hilbert space is the only framework that stays organized, even when the math grows to include trillions of different paths. To actually run a calculation, scientists apply quantum gates. Think of these gates as the pianist's fingers, carefully rotating and transforming those arrows across the math space without breaking the rules of the grid. Eventually, the calculation finishes, and the scientists must read the result. Measuring a qubit forces all those swirling, overlapping probabilities to instantly collapse into a single, definite basis state. It is like the heavy felt dampers pressing down onto vibrating piano strings. The complex symphony abruptly stops, leaving you with one clear, measurable note. Without this rigorous coordinate system in place, all of those overlapping states would be nothing more than uncontrollable noise. So when researchers build machines to solve problems that regular computers cannot touch, they are essentially conducting a highly precise symphony. And Hilbert Space is the sheet music making it all possible.